The next paper in our schedule is dRR, a decentralized, scalable, and auditable architecture for RPKI repositories. I take it you're the speaker?
Yeah.
Wonderful. I will let you introduce yourself, and there's a mic there on the podium.
Okay.
Yeah. So this should advance your slides.
This.
Yes. Do we have slides for him? Just a minute. There we go.
Oh, okay. Okay, hello everyone. I'm Lan Chengqin from Tsinghua University. So actually, I will do my presentation tomorrow morning, but the authors of this paper cannot attend this on-site meeting, so I will do this presentation for them. Okay, so this work proposes a new RPKI repository architecture called dRR. So it aims to improve the security and scalability of existing RPKI. So RPKI is standardized by IETF to prevent prefix hijacking in interdomain networks, and is a hierarchical architecture that distributes and manages rules. And there are many important comments in RPKI architecture. The CA or RPKI authority can sign resource certificate and route origin authorization rule to INR holders. The rule authorizes ASs to originate specific IP prefixes. And each CA runs a publication point to store RCs and rules issued for INR holders. All PPs collectively form the RPKI repository. The relying parties periodically traverse all PPs and download and validate all RPKI objects, and then they generate verified rule payloads to help border routers making routing decisions. And there are three problems of existing RPKI repository. The first problem is unilateral reliance on RPKI authority. RPKI repository is not tamper resistant. Authorities can unilaterally undermine any RPKI objects without INR holders' consent. The problem two is vulnerable to single point of failure. Any PP's failure will hinder IPs from obtaining complete RPKI object views. Oh, sorry. And problem three is poor scalability. It means IP local cache refresh involves traversing all PPs to fetch updated data. But the number of PPs is expected to increase dramatically with the future deployment of rule. So the three problems will affect the integrity and accuracy of the stored RPKI objects and hidden future large-scale RPKI deployment. In this work, we first propose the first data-driven threat analysis for RPKI repository. As mentioned above, the problem one and the problem three are identified through a worldwide survey, and problem two is identified from an RPKI repository measurement. Okay, for problem one, we conduct a large-scale survey among AS operators, and we found more than 44% of the AS operators express concerns about malicious authorities. Specifically, one operator considers the threat from authorities to be the most serious problem. For problem two, although RDP suggests to deploy PPs in CDN infrastructure, but our measurement shows only 8 PPs are hosted in CDNs, and 48 PPs are hosted in a single AS, and 14 PPs carry the error of the ASs they located. In this case, the accessibility of PPs will form a circular dependency on the reachability of ASs. So any single point of failure in PPs may hinder RPs from obtaining complete RPKI object views. For the problem 3, we can see the number of PPs has grown more than 12 times since the beginning of RPKI deployment. And recent researches show if ROA is fully deployed, the number of PPs will reach 10,000. The rapid deployment and the development of RPKI will bring some potential problems, such as the scalability of RPKI, the cost of RP refreshing, and some unexpected risks to RPs. So to address the problems, we propose dRR. The key idea of dRR is separating RPKI object distribution from sign. To address problem 1, dRR aims to defend against RPKI authorities' malicious behavior, and all IPs will verify certificate status, and all INR holders verify the integrity of RPKI views. In this way, RPKI historical data can be audited. To address problem 2, dRR should defend against single points of failure and provide truly distributed data storage to guarantee that PP accessibility is independent of AS accessibility. To address problem 3, dRR should prevent unlimited growth in the number of PPs to improve the reliability of RPKI repository system. In addition, dRR should be compatible with RPKI architecture and supports incremental deployment. Okay, this figure shows the architecture of dRR. As shown in the figure, dRR has two new entities. They are CS Federation and Monitor. The CS Federation replaces the RPKI repository to help IR holders store certificates, and Monitor provides verifiable certificate updates list for RPs. Specifically, certificates are no longer stored in the PP running by RPKI authorities. INR holders can choose the CS nodes in Federation they trust to provide certificate hosting services for them. The issuance and revocation of each certificate is accompanied by signing of the certificate issuance policy or certificate revocation policy. The defined certificate policies can provide proof that the relevant CAs and IR holders have confirmed the issuance or revocation of the certificates. All the certificate policies will be publicized among the CS members to show the operations are widely recognized. Once a majority of CS nodes agree on the policies, the certificate will be published or deleted successfully. Based on the certificate issuance or revocation policies, the Federation can maintain a widely recognized RPKI object global ledger for auditing. Furthermore, CS nodes will push the newly added certificate policies to Monitor, and then monitors can update their local M tree data structure. Based on M tree, RPs do not need to traverse all PPs to check certificate updates, but instead periodically get verifiable certificate update list from monitor. And then they fetch the new certificates and delete the old ones accordingly. So overall, dRR will address the above 3 problems. For problem 1, in dRR architecture, INR holders can freely select trusted CSs to host RC or ROR. And CRPs and CRPs provide a trusted RPKI historical ledger, and the M-tree data structure can well meet the security requirements of RPs and INR holders. For problem 2, in dRR architecture, one certificate can be hosted on multiple CS nodes, so it can improve the scalability. For problem 3, the access mechanism effectively limits the number of CS nodes. So dRR with the 5 properties that can well improve the security and scalability of existing RPKI repository. We also evaluate dRR on a global testbed. The global testbed, here we select 100 server nodes across 15 countries. And we use 15 nodes for the CS federation and 15 nodes for monitors. We mainly consider the 2 performance metrics. One is the throughput of CS federation, and the other is their additional latency introduced by dRR. Our evaluation shows the throughput of CS federation can reach 300 or more than 300 per second, which is about 450 times of the existing RPKI repository, and the delay introduced by CS federation is less than 2 seconds. As for the monitor, the delay introduced by monitors is less than half 1 second. Considering the bottleneck of existing RPKI repository is certificate signing or synchronization, which usually takes tens of minutes to several hours. So the latency introduced by dRR is very small. In summary, in this work, we first propose the first data-driven RPKI threat analysis and describes the 3 problems of existing RPKI repository. And then we propose the first RPKI compatible design to enhance the current vulnerable RPKI repository. And then we implement a prototype of dRR and evaluate a global testbed with 100 nodes. Okay, thank you everyone. Because I'm doing this presentation for the authors, if you have any questions, you are welcome to contact them via email. Thank you.
Yeah, let's thank our speaker.